So essentially, we derived the expression for a convex mirror as 1 over s minus 1 over s prime is equal to minus 2 over r. Now, if we want to do this for a concave mirror, what you have to realize is that for a concave mirror, the image distance is the other way around, because in case if you look at say parallel rays of light falling on a concave mirror, so if I have one ray here and that gets reflected here, and another ray that is coming here, it gets reflected back and they meet here, right? So the image distance is going to be positive for a concave mirror. So now then we would have, this is for convex. So all that you need for a concave mirror is to change the sign. So you would have 1 over 1 plus s is equal to, so this is for a concave mirror, right? So again, we call the sign conventions. The object distance is positive if the object is to the left of V. So in the first example, that in the first thing that we did, that's a convex mirror, right? We considered the object here to the left, right? That's why S was positive, right? And when object is to the right, it is negative. But in this case, we are considering for both convex and concave, we are considering object to be on the left, right? So, sorry, this should be image. And when the image is to the left, again, the distance is positive. So in case of a concave mirror, the image is forming onto the left as well, right? And that's why you have here a positive sign. We change the sign here for a concave mirror, because so we change the sign here because for the concave mirror, both object and image are on the left side. So the object distance is positive if the object is on the left, and the image distance is positive if the image is on the left, right? And the radius of curvature is positive when the center is to the right side of V, right? So when the center is to the right side of the vertex, right? So in case of a convex, we have a positive radius of curvature, and in case of a concave mirror, we have a negative radius of curvature. So in general, we can write the mirror as mirror equation as 1 over s plus 1 over s prime is equal to 1 over f, where we're defining f as the focal length as r over 2, negative r over 2. And this negative r over 2, again, notice that here I have not changed the negative sign between the convex and concave. And this would be greater than 0 if I have a concave mirror, because for a concave mirror, the center is onto the left side. So the radius of curvature would be written as a negative number. So for a concave mirror, this would be greater than 0. Whereas for a convex mirror, this would be less than 0 because the center of curvature is to the right, right? So please pay attention to these sign conventions. So here we have not changed the negative sign, because depending upon whether it is a convex or a concave mirror, you would write r as a negative number or a positive number. For convex, you would write r as a negative, r as a positive number. So because if I write r as a positive number, minus r by 2 will overall be a negative number. So for a convex mirror, minus r by 2 would overall be a negative number. On the other hand, for a concave mirror, because the center of curvature is onto the left side, right? Center of curvature is onto the left side, we would write r itself as a negative number. And so minus r by 2 would be positive because I'm writing r as a negative number. So negative times negative gives me positive. So the focal length for a concave mirror would be greater than 0. And in general, for spherical surfaces, we can write this as 1 plus 1 over s plus 1 over s prime is equal to 1 over f. Now we can see if I have a plane mirror, the radius of curvature is infinity. So focal length is 0, right? So 1 over s is equal to minus 1 over s prime. Or if you're standing a few feet from the mirror, it would appear as if your image is standing the same distance behind the plane mirror, right? So in this way, we are able to validate from the spherical by making r is equal to infinity approximation. We are able to verify what we have seen in the case of a plane mirror. Now let's look at, instead of point object, if I have an object that's of a height h0, if I have an object that is of an height h0, now then again, to look at how the image forms, we would draw two rays, right? So the first ray that hits from the top of the object, it hits the vertex V and it is reflected, and these two angles are equal, theta I is equal to theta R. And another ray that is coming here is reflected right back, right? So if I extend these two rays, right, this is how the image would form. Because this is not a point object, this is an object, extended object with a height h0, my image would also have hi. Again, here I'm extending diverging rays behind the mirror, so the image is virtual here. Please think about that, why the image is virtual here. So by looking at these two triangles, the first triangle is this one with the image, and the second triangle is this, right? You can see that these triangles are similar. So if I were to look at this angle, right, then this distance is the image distance, this is the object distance. So if I look at the tangent in the first triangle here, the tangent would be h0 divided by s. In the second triangle, the tangent would be hi by s prime. And because these are similar triangles, the angle is the same. Because the angles are equal, we can see that h0 over s is equal to hi over s prime, right? And we can define something called magnification. So magnification is defined as the image height by object height, and in this case it would be s prime over s. From here, right, from here I can write h0 or hi over h0 as s prime over s. So I can write magnification as s prime over s, right? Convince yourself that these two triangles are equal. Don't be confused here. Here this and this are not at right angles. Okay, so don't be deceived by how it appears. They are not at right angles. So if you see this angle is theta r, so this angle should also be theta r, right? And so this angle is same as the incident angle here, and that's why we have similar triangles, because this is right angle and these angles are also the same, right? So this is not a right angle necessarily. It looks like that, but it is not necessarily a right angle. Okay, so we have looked at the mirror equation, 1 over s plus 1 over s prime is equal to 1 over f, and be very careful about sign convention. And we have looked at the magnification, which is s prime over s. So now let's do example problem, right? So here we have an object which is 3 centimeters high, and it is placed 20 centimeters. Let's start with a convex lens. It is placed, sorry, not a convex lens, but a convex mirror, which has a 10 centimeter focal length. So we have 10 centimeter focal length for the convex mirror, and we are given that the object is 3 centimeters high and is placed 20 centimeters. What we have to do is determine the position and the nature of the image, right? What is the nature of the image in a convex lens? We have just seen this. The image is virtual, but let's just use the equation. We have seen that the image is virtual by tracing the rays, and we have seen that the rays are actually diverging, so we have to sort of extend them behind the mirror to view an image. That's how we identified that the image is virtual. But let's use the mirror equation to see how this virtual image jumps out at you. So we know that the mirror equation is 1 over s plus 1 over s prime is equal to 1 over f, right? So if I place the object onto the left of the mirror, then I can consider this as positive distance, so 1 over 3, right? Plus I don't know the image distance, so I'm going to say 1 over s prime. For a convex lens, the focal length is going to be for a convex lens, the focal length is going to be, right, the center of curvature is to the right. And remember, we defined focal length as minus r over 2. So focal length for a convex lens is going to be less than 0, because we are considering the center of curvature on the right side. So the focal length is negative. So here we would have minus 1 over 10, right? And oh sorry, this is the height of the object. The distance of the object is 20. So then if I want to determine 1 over s prime, I have minus 1 over 10 minus 1 over 20, right? I can write this as minus 2 over 20, or I would have minus 3 over 20, or that implies s prime is equal to minus 20 by 3 centimeters, right? So now you can see that s prime came out to be negative. That means this image should be virtual. Whenever the image distance is negative, that means the image is virtual. Look here, we have considered a positive distance because the object is real, and we got a negative answer here. So the image is virtual image, which we know it should be virtual because it's a convex lens. Now let's do the same thing for concave lens, right? We're going to do the same thing for a concave lens. I keep saying lens, I apologize. It's a force of habit. It's a mirror. It's not a lens. It's a concave mirror. Sorry about that. So in case of a concave mirror, again, we know that object distance is 20 centimeters, and we need to find out s prime. So in case of a concave mirror, the focal length, we know that minus r by 2, right? In case of a concave, the center of curvature is to the left, so we need to write focal length as greater than 0, or focal length as a positive number, because the center of curvature is on to the left, and we consider light to be propagating from left to right. So anything on the left is positive, anything on the right is negative. So then if sorry, anything on the left is negative, anything on the right is positive. So we are writing this as minus r over 2 greater than 0. So the focal length would be plus 10 centimeters in this case. So if I apply the same equation, 1 plus s prime is equal to 1 over f, I would have 1 over 20 plus 1 over s prime is equal to 1 over 10, which implies 1 over s prime is 1 over 10 minus 1 over 20, right? So that would be 2 minus 1 by 20, or that is 1 by 20 centimeters, and we got this as a positive number. So what do you think? Is the image real, or is the image virtual? We got a positive number for the image distance, so s prime is equal to plus 20 centimeters. So that means the image is real. Whereas in case of a convex mirror, the image is virtual, right? And once you have the object and image distances, you can determine the magnification. Recall that we have derived a magnification equation, right? So the equation for magnification is m is related to s prime over s, right? So m is equal to m times n. 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 So So we can look at what the magnification is. So the image distance is 20 centimeters, the object distance is 20 centimeters, so the magnification is going to be -1. So -1 means that the image is going to be inverted. If the magnification is positive, the image is erect, and if the magnification is negative, the image is inverted. We did not go through magnification in great detail, but I would take this up again in the next lecture. Meanwhile, I would like you to go through this part in the textbook and see how to use the sign conventions. It is very easy to get confused, as you have seen me. So don't be confused by the sign conventions. Going from left to right is positive, right? Image distances are positive if the image is real. Image distances are negative if the image is virtual. And if the center of curvature is to the right, then we consider the radius of curvature to be positive. If the center of curvature is to the left, then we consider the radius of curvature to be negative. So the focal length for a convex mirror which has the center of curvature to the right is negative, because we define focal length as -r/2, and that r is a positive number. So overall the focal length would be a negative number. Whereas in case of a concave mirror, the center of curvature is to the left, so we consider that distance to be negative. So focal length, which is -r/2, and if r is negative, overall negative times negative, focal length would be positive, right? And by using the equation 1 over s plus 1 over s prime is equal to 1 over f, and following the sign conventions correctly, you can see whether the image is virtual or real, and by looking at the sign of the image distance. Okay, thank you.